Hi there, I'm Paolo Pani from Sapienza University of Rome, but today I'm recording this talk from the wonderful island of Sardinia. You can see a picture here of the place where I am with a small version of Lisa flying over the Sardinian Sea. So I cannot complain too much that is in these unfortunate times the Lisa Symposium was online. I'm going to present an overview of tests of the nature of compact objects with LISA, and the bottom line of my talk is that LISA has a superior capability to constrain exotic compact objects and to search for new physics in compact objects. First of all, I will try to motivate why these studies are important, and the main reason is that the current paradigm is that any compact object heavier than a few solar masses must be a black hole, and in particular almost all LISA sources are supposed to be black holes. Any observation telling otherwise or providing evidence of otherwise would imply some new physics or some new matter fields, and anyway the existence of what I would call exotic compact objects, so something that is not a black hole nor a neutron star, a different compact object. There are many motivations to study exotic compact objects, and the first one is that black holes and neutron stars might just coexist with other species. Exotic compact objects might explain exotic events, for example, LIGO-Virgo mass gap events, both in the low mass range and in the high mass range, might be explained by objects which are not the standard ones that we expect. Another motivation is that E-codes can form within GR with new matter fields, so you don't need to modify gravity, but even in the presence of extra fundamental fields that will augment the standard model particle physics, for example axions or ultralight bosonic fields, they might form self-gravitating objects. A more theoretical motivation is that black holes by themselves have some theoretical issues. It's related with the singularities in their interior and also with the famous information loss paradox that is related with the fact that quantum effects near the horizon are problematic. And these really fundamental problems might be resolved either assuming new physics at the horizon scales, for example like in the firewall proposal, or if regular horizonless compact objects exist, as in the Fatsball proposal, in which there are microstate geometries that are regular, horizonless, and can account for the huge entropy of black holes. There is a very last motivation, which is even if it turns out that there are no exotic compact objects or no other species of compact objects, we can at least quantify whether LISA sources are really black holes or not, and we need to find a metric to quantify this test. So exotic compact objects exist in many different flavors. There is an entire zoo of them. I think that they belong basically to two categories. The first one is solutions to general activity with exotic matter sources, and in this class are anisotropic bosons, anisotropic stars, neutron stars with anisotropic stresses, or boson stars, stars made of bosonic fields, axion stars made of axions, or the so-called grava stars, or even more exotic objects like wormholes. They require exotic matter fields, whereas in the second category there are solutions to modify gravity which might not require exotic fields. For example, wormholes in modified gravity exist even in the presence of perfect fluid matter. Solution to the second category includes Fatsball and microstate geometry to two holes, superspinors, object which spins faster than the Kerr black hole, and so on and so forth. In some cases, the distinction between these two categories is not that sharp, because you might have objects in one category or in the other, or you can treat exotic matter by modified gravity effect. The good thing is that in some cases, exotic compact objects require modified gravity only very close to the would-be horizon or within the object, and therefore in many cases assuming GR in the exterior is a good approximation. So here I'm not going into any detail of these models. For this, I refer to this living review that we recently worked together with, wrote together with Vitor Cardoso, and I will focus only on the phenomenology of LISA in an agnostic way. So I will not assume any specific model, at least for most of my talk. So let me start by say how can we quantify the black holeness, so the shade of darkness of a compact object. So there are essentially at least two parameters which can define a black hole. The first one is the compactness. So we can define a radius or an effective radius of a compact object, and in this case I will define the radius in this way. So as the location of the event horizon in a given set of coordinates times a parameter epsilon that goes to 0 in the black hole limit. The second dimension in this diagram is the reflectivity. So we know that black holes are very compact and they are black in the sense that they reflect all radiation of any kind that is thrown into the horizon. So in this two-dimensional diagram, black hole sits here when epsilon is 0 and when the reflectivity is also 0. In this parameter space, we can identify at least four regions. The first one is relatively small compactness without assorption. So here on the top right, this is the typical regime of boson stars, which are not that compact. They have the same compactness of neutron stars, but definitely not as much as a black hole. Then there is a regime in which the compactness is of the same order, so it's not that large, but objects are strongly absorbing. And this is the case of what is sometimes called diffuse fastballs. Then there is also another corner in which there are large compactnesses and no absorption. So these objects are almost as compact as a black hole, but they do not absorb radiation. They might be even perfectly reflecting. An example are Grava stars, at least in some models. And finally, there is the regime which is more difficult to probe, where the objects are as compact as a black hole and they absorb almost as much as a black hole. So they are very close to the black hole limit here. And of course, the goal of phenomenology is try to constrain this parameter space, possibly down here close to the black hole regime. I will focus on gravitational wave-based tests. There are also a lot of electromagnetic tests that one can do, and in particular I will focus on the coalescence signal. And as nicely summarized in this slide that I stole from a concept by Tania Hindren and Andrea Maselli, there are different phases in the inspiral merger ring-down waveform and post-ring-down waveform that can be used to constrain different properties of exotic compact objects. So at the beginning, everything works like two-point particles. There are no signatures of the nature of this object. But while the inspiral proceeds, tidal effects starts becoming important, spins deformation starts becoming important, all the multipolar structure of the objects become important, and also the fact that they absorb radiation. So all these effects enters a different post-Newtonian order. The merger is highly non-dynamical and model dependent, so it will also show differences there. And in the post-merger phase, there might be different ring-down modes or the so-called echoes. So I'm gonna discuss all these effects in some details and point to other talks that are available online on this symposium. So let me start with black hole spectroscopy. So we all know that the prompt ring-down signal right after the merger, or sometimes after the merger, can be described as a superposition of quasi-normal modes. These are just damped sinusoids with a frequency and a damping time. LISA rates for supermassive black hole coalescences are uncertain, but we expect at least a few events with very high SNR of the order of the hundreds. For these events, the frequency and damping times of several modes can be detected, and so black hole spectroscopy can be made. In particular, a recent development is that black hole spectroscopy might also take advantage of the use of the detection of overtones, and there are at least two talks by Cecilia Chirenti and Shweta Bhagwat in this symposium about this interesting topic. In the context of exotic compact objects, some smoking guns in the prompt ring-down are three at least. One is mode shift, so this frequency and damping times changes depending on the objects, of course. There might be extra modes due to matter fields or extra polarizations, although a very important open problem is how big are the amplitudes of these extra ring down modes, so whether they can be excited significantly in a merger. And finally, isospectrality breaking. So we know that the modes of a Schwarzschild black hole, and in some sense also of a Kerr black hole, are isospectral, so axial and polar modes, even and odd parity modes, are isospectral, while this is not true anymore for any kind of star, any kind of object beyond the Schwarzschild and Kerr case. So if you want to know more about this effect, and in general, if you want to know how does a dark compact object ring down, I suggest you either to read this paper or to attend the Lisa Maggio talk on September 3rd during this symposium. Actually, do both. In the later ring down, there are also other effects. So we know that for ultra-compact exotic compact objects, so for ultra-compact objects, when epsilon is smaller than around 10 to minus 2, the prompt ring down is identical to that of a black hole, but there might be new features in the form of gravitation wave echoes at late time. This was explored in a series of papers, and here I just want to mention that anytime a compact object does not have an horizon but is sufficiently compact as to form a light ring, the situation for the perturbation is depicted in this effective potential here. So there is a maximum given by the photon sphere of the object, and if there is no horizon, some of the radiation that is contained in this cavity here is doomed to be reflected and go to infinity in the form of exotic compact of echoes. Indeed, when you compute the ring down of one of these objects with an effective potential of this form here, either a gravitar star or a very compact object without a horizon, you'll see that the waveform has this form here. So the prompt ring down is identical, and then is followed by a series of modulated train of pulses that is just radiation going back and forth here. This might happen if the object has a stellar-like interior. In such case, there will be a centrifugal bar here. If there is some sort of fuzziness in the space-time, in the sense that this interior does not behave as a classical horizon, or if there is quantum emission from the horizon itself. So the point I want to stress is that echoes are very generic anytime you don't have a classical horizon. Yet it's quite involved to model properly. The signal here is a transient signal with a lot of features. There has been a lot of progress in waveform modeling of echoes. There is this nice overview here, and also a talk by Nayesha Shorty during this symposium. I just want to mention that the delay time between echoes scales logarithmically with this parameter epsilon, and keep in mind this fact because it will be recurrent during this talk. How about that echo detectability with LISA? So the signal depends strongly on the reflectivity of the object. Here I'm showing the LISA sensitivity curve versus the echo signal and the standard ring down signal. You see that depending on the reflectivity of the object, you might get very sharp feature or much more mild ones. And this reflects into the fact that it's much more easy to constrain objects which are almost perfectly reflecting, so when there is reflectivity is of order unity, than objects which are almost perfectly absorbing, so they behave like black holes. These results here, which show the constraints that can be put at 2 sigma, 3 sigma, 4 sigma confidence level, depending on the SNR in the ring down of various detectors, were obtained with a physically motivated analytical template in the frequency domain that contains a lot of interesting effects that I'm not gonna discuss here. I just want to mention that if you want to reach really the black hole limits, so constraints, search for or rule out exotic compact objects with very small reflectivity, then LIGO, but even to a certain extent 3G detectors are not enough. LISA ring down SNR is really crucial to be able to reach this level of accuracy here and essentially ruled out even very small reflectivities. If you're interested in this topic, waveforms, templates, movies are available on our group webpage. Let me now go to the inspiral. So the inspiral can be, at least of comparable mass binaries, can be modeled with Post-Newtonian theory. There are different phase terms in which the nature of compact object is encoded. The first term is the point particle phase, and the point particle phase depends on the masses and spins, of course, but also on the multiple moments of the bodies. And this is very a nice feature to try to measure the multiple moments and test the black hole no-hair theorems. So we know that a Kerr black hole has infinite multiple moments, both mass and spin, but they are all related to each other through this elegant relation in terms of only two parameters, the mass and the spin of the object. So a black hole, when non-spinning, is spherical, when spinning has these funny embedding diagrams, even though this is a sort of extreme case, but it's also very symmetric. Now for ecos, this is not true anymore. Ecos might have all multiple moments possible, and in general they will have the multiple moments of a Kerr black hole plus corrections. There are estimates that LISA can constrain at least the mass quadruple moment M2 and the spin octuple S3 with detection of essentially supermassive black hole coalescences. Now, an interesting property is that if you study quite generically within a GR context these corrections here, delta M and delta S, it turns out that in the black hole limit they go to zero with a certain scaling of the compactness, and this is what we call in this paper a hair conditioner for black holes. So there are hairs, but they cannot be arbitrarily large, and in fact they go to zero either logarithmically if they are spin-induced or linearly if they are not spin-induced. And again, there is this logarithmic of epsilon appearing here, which is very convenient because it means that the correction to the multiple moments are not extremely small even when epsilon is actually tiny. There is even more than that, because the results I was mentioning before, so these ones here, assume axisymmetry, like in the Kerr case. But in fact, an exotic compact object does not need to be axisymmetric, and in fact, stationary eco solutions exist which break equatorial symmetry and also axial symmetry. So they might have moments like S2 and M3, or even actually moments which form a tensor because they are not axially symmetric. This was shown very recently for fast balls. There are solutions that we derived in these papers here which break all symmetries, and very recently, actually today, at the time of recording, there has been a paper by Carlos Herrero and collaborators showing that something similar exists for Boson Stars. So it's very interesting that current waveform models do not include these higher order and also different multiple moments, and should be extended to accommodate for them. Fast balls in this respect have very nice features because these multiple moments can be combined in certain ratios which are sort of universal depending on how one takes the black hole limit. This was shown in these two papers here by Joseph Ben and Daniel Meyerson, and Daniel Meyerson has a talk in this symposium about this. Also, certain multiple invariants constructed out of these multiple moments are minimum for the black hole case compared to the huge family of fast ball solutions that exist, and this is another way LISA can look for fast balls, or anyway constrain them by looking at whether the multiple moments are bigger than what is expected for a Kerr black hole with a given mass and spin. Another effect that enters, so the effect of the multiple moments, the quadruple moment at least, enters at 2pn order in the waveform, and higher moments enter at higher orders. The tidal heating term, so the fact that a black hole can absorb radiation, enters at a higher order, so it's a 2.5 times log v, where v is the orbital velocity correction. The nice thing is that a black hole has this term. An exotic compact object typically does not have absorption, so in this respect is very similar to a neutron star, and therefore this term is absent, or anyway much smaller. Being a higher order post-Newtonian term is a small effect that is possibly not even measurable by 3G detectors. It will require LISA binaries. And there are studies showing that if massive black hole binaries that are highly spinning merge at relatively short distance, so close to us, at about 10 gigaparsec, this can be measured by LISA. So this effect, the tidal heating, can be measured by LISA. This was shown by us in this paper here. And EMRIS, in EMRIS, the tidal heating term is much stronger, and in fact is much easier to constrain this effect in EMRIS with LISA. Finally, the last term in the phase is a 5PN term that depends on the tidal deformability through the law of numbers, so the fact that these objects can deform each other during the coalescence. And a nice property of black holes is that at least static black holes in general activity have zero law numbers, so they do not have such term in the waveform. This was extended recently to the spinning case, assuming axis symmetry, and very recently it was shown by Alexander Letiek and Mark Casals that is not true for beyond axis symmetry. So there are non-axis symmetric law numbers which are non-zero for a Kerr black hole, and I suggest you to attend Letiek talk about that. Anyway, either if they are zero or small, they are fixed quantities, just like the multiple moments. And for an exotic compact object, this is not true anymore. They are generically non-zero, they are generically large, much larger than possibly even in the black hole case, so they can be used to as a baseline to develop tests of the tidal deformability of LISA binaries. And in fact, it was recognized in previous papers that the tidal deformability can be used to search for echos and black holes in modified gravity with LISA binaries. I'm saying LISA binaries because it's a small effect. LIGO can constrain certain boson star models, for example, and in general exotic compact objects which are not too compact, but LISA has really the huge potential to distinguish black holes from any boson star models known so far, just because the tidal of number of boson stars are large enough. Even more, the law of numbers of certain exotic compact objects, the most compact one, scales again logarithmically with this parameter epsilon, which is again fortunately because it means that even if epsilon is super small, this lambda is of the order 10 to minus 2, 10 to minus 3, which is more or less in the ballpark of LISA sensitivity, depending on the, the event rates of supermassive mergers. But there are studies, in particular the one that I mentioned before by Maselli et al. In 2017, that show how LISA can be able to put constraints on this parameter epsilon here, even when the distance from the horizon is microscopic, because essentially it can reach levels for the constraints on the log number of this range here, 10 to minus 2, 10 to minus 3. So far I talked about all these effects separately, but in fact for a given exotic compact object model, all these effects are related to each other, so they are not independent, but tidal heating, the multiple moments, the tidal deformability, all will depend on the binary masses and spin and on the complete constant of a given theory. So if you take your favorite model, you don't have that freedom to turn on the multiple moments and not the tidal heating or vice versa. And this is clear for boson stars. So for boson stars, you can start with a theory like this, general relativity with a scalar field and some coupling constant for the scalar interactions. And this is all you need, together with masses and spin, to know everything about the inspiral of your object. And recently, with Costantino Pacilio and collaborators, we worked on the first coherent inspiral model for boson stars. I suggest you to attend Costantino's talk if you want to know more. This model puts together everything in a coherent way, and what we found is that a coherent model significantly improves the constraints. The main source is the tidal deformability, as expected, but putting everything together gives much stronger constraints. And again, here we need LISA for this kind of test, because the constraining power of current detector is marginal. With third generation ground-based detector will start getting interesting constraint, but with LISA we get an order of magnitude better than with rigid detectors, so we can really constrain any boson star model with a coherent inspiral waveform. Finally, a few words on extreme mass ratio inspiral, last but not least, because EMRIs are really unique probes of both the multipolar structure and the dynamics of a theory or of a model, and in fact all ECO's features are amplified in extreme mass ratio limits. For example, there are studies showing that there are incredible constraints on the spin-induced multiple moment. In particular, the quadruple moment can be constrained order of magnitude better than with current detectors. The tidal heating, which is so difficult to measure for supermassive binaries, can be constrained very well, especially with highly spinning objects. So if the EMRI is around a supermassive highly spinning object, we can constrain the reflectivity of the object at the level of 1 part in 10 to minus 4, which is impressive. And even the log number, so if the central object, the supermassive object, has a tidal deformability, so it's not a black hole, or maybe it's a spinning black hole, so that it has some tidal log number, we can constrain that tidal deformability parameter at the level 1 part in 10 to minus 5. This is a preliminary study using Newtonian theory, and of course it can be extended in many ways, but the ballpark of the constraint should be that one. So all in all, this shows that there is a huge potential for LISA to constrain exotic compact object models with extreme mass ratio inspiral. Finally, it is also possible to test the Kerr bound, so the fact that the spin of a Kerr black hole is bounded from above, cannot be bigger than 1, this dimensionless spin chi, and pretty much model dependent and anyway much simpler and accurate way to test this Kerr bound as compared to the case of supermassive binaries or anyway post-Newtonian bounds, can be done with EMRIs if one can measure the spin of the secondary object. And this is studied in these two papers here, and if you're interested in this, please attend Gabriel Piovano's talk on this subject. All of this is very preliminary constraints. There are a lot of assumptions there, simplifications, both on the theory side and on the data analysis side. So there are challenges in the modeling, in the parameter estimation, etc., which must be overcome for sure in the years to come. But this really shows that there is huge potential to constrain this. So let me come to my conclusion. LISA has really a superior potential as compared to any other detectors to search for departures from the classical black holes. There is a huge discovery opportunity for new physics and for the existence of new species of compact objects. Even if you want to be conservative, at the very least, we'll have orders of magnitude improvements on current constraints on the black holeness of compact sources. And at the same time, during the last few years, there has been a dramatic improvement on understanding and developing on the theory of exotic compact objects on all fronts, both in the level of becoming more mainstream, but also modeling, theoretical understanding, and so on and so forth, simulations, etc. We can do much better in all fronts as well, in terms of simulations, especially studying the coalescence and modeling the inspiral merger ringdown waveforms of exotic compact objects, in particular Boson star binaries. And there are also theoretical issues that we want to understand better, a comparison with other constraints, for example, coming from electromagnetic observations. Finally, some of these models are related with quantum gravity. For example, fastballs or other proposals are meant to arise from modified gravity, supergravity theories, and string theory. If we want to test quantum gravity, which means that these objects have some Planckian correction in one way or the other, we really need some correction that scales logarithmically with Planck scale. Fortunately, there seems to be many different properties of exotic compact objects that show up in the waveform, which have these specific logarithmic scaling. So we might get lucky if we want to be optimistic and learn something from quantum gravity with gravitational wave observation. I think I'll conclude here. I thank you for the attention, and I will leave you with this link here with a comprehensive living review, which will be hopefully updated in the future, that contains all the description of the effect that I mentioned, the caveats on the models, the constraints, and a big list of references that I could not include here for lack of time. So thank you for the attention and enjoy the rest of the symposium.